Hey everyone, welcome back to the Embedded Systems Programming from Scratch series. In the last few videos, we made the ATSAM3 X8E blink the onboard LED using C. Now we're starting the same journey in assembly. We'll see how all those C instructions actually translate down to low-level operations on the ARM Cortex-M3 core, and how we can control hardware registers directly using assembly instructions. Let's get started. Alright, first I'm going to set the assembly syntax and target CPU. This tells the assembler we're using the modern unified syntax, targeting the Cortex-M3 processor, and working in thumb mode, which is what the SAM3 X8E uses for better code density. Unified syntax allows you to write assembly code that works correctly for both ARM and thumb instruction sets, using a single consistent set of mnemonics and operand order. Now I'll add the constants for clock and delay calibration. Here I define the CPU frequency as 84 MHz and calculate how many loops we need for roughly 1 millisecond delay. We'll use this later in our delay function. Now I'm going to define the registers and bit fields. They are the exact same registers and bit fields we used back in the C videos. Since I already explained them there, I'm just gonna quickly define them here. Now let's get into the actual code. That text tells the assembler, hey, everything after this is executable code, not data. All the functions, all the instructions, everything we write here from down, that's code. Then, .thumb_func tells the assembler the function that coming up next is thumb mode code, which the Cortex-M3 requires. And .global makes this label board_clock to 84 MHz visible to the linker, so we can call it from the main later. Let's write the function itself. This function is responsible for configuring the board clock to run at 84 MHz. First instruction inside the function. This is the function prologue. We're saving registers R4 through R8 and the link register onto the stack. Why? Because the ARM calling convention says a function has to preserve R4 through R11. If we're gonna use R4 to R8 inside this function, and we will a lot, we have to save their original values first so we can restore them when we're done. The calling function might be relying on them. And we push the link register too, because even though this function doesn't call any other functions, we still need LR to return. The link register is register R14 in ARM processors. Its job is simple. It remembers where to return after a function finishes. At the end, we'll pop it straight into the program counter, and that's how we jump back to the main. The stack pointer adjusts automatically. Push those 6 registers and the stack grows downward by 24 bytes. Next up, we set the flash wait states. First, we load the EEFC0_FMR address into the R0. Then, we load EEFC_FMR_FWS, the wait state value, into R1. Next, we need to write that value into the flash mode register. STR is short for store register. It takes whatever value is in R1 and writes it into the memory address stored in R0. The square brackets around R0 mean use this as a pointer, not the value itself. So we're not writing to R0, we're writing to the address that R0 points to, which is the flash mode register. And we do the same for EEFC1_FMR. Now we check whether the external oscillator is already selected. If it's not, we need to enable it. First, we load the address of the main oscillator register into R0. Now we read from that address and put the value into R2. And we load the MOSCSEL bit mask into R3. That's bit 24. which indicates whether the external crystal oscillator is already selected as the clock source. And TST is short for test. It performs a bitwise AND between R2 and R3 but doesn't store the result anywhere. It only updates the condition flags. If bit 24 is set, the 0 flag will be clear. If it's not set, the 0 flag will be set. The 0 flag is a bit inside APSR, the Application Program Status Register, which is part of the CPU core itself. The next instruction will check this bit. BNE means branch if not equal, which is the same as branch if the 0 flag is clear. So if MOSCSEL is already set, we jump ahead to main_OSC_selected. We'll write that part soon. And we skip the whole oscillator enable sequence. If it's not set, we follow through and enable it ourselves. Alright, let's continue and enable the external oscillator. First we load MOR_key, MOSCXTSD, MOSCRCEIN, and MOSCXTEIN into registers R4 through R7. Now we combine all four values into a single configuration using OR instructions, building up the final value in R1 step by step. Then we store R1 into the main oscillator register, R0. Next, we wait for the crystal to actually stabilize. We create a label. This is our polling loop. First, I load the address of the status register into R0. Then read its value into R2. And I ended with MOSCXTS bit mask. Now here, we need to check the result of that operation. BEQ means branch if equal, which is branch if the 0 flag is set. So if the crystal is not stable yet, MOSCXTS will be 0. The TST will set the 0 flag and will branch back up. We just spin here in a loop until the bit finally goes high. Once MOSCXTS is set, the 0 flag will be clear. BEQ won't branch and we fall through to the next instruction. The crystal is ready. Next, I create the main_OSC_selected label. This is where we end up whether the oscillator was already selected or we just enable it. Either way, we now switch the system to use it. And we need to make sure the switch actually happened before we move on. So we pull the status register one more time. Now that the external crystal is selected and running, we configure the master clock to use it. First, we load the master clock register address into R0 and read its current value into R2. And I load the clock source mask into R4. That mask covers bit 0 and 1, the CSS field. Then we flip every bit with MVN, move not. The two bits that were 1 become 0 and every other bit becomes 1. And we end this inverted mask with the current register value. That clears just the CSS field to 0 and leaves every other bit exactly as it was. Next, I load the value for the main clock selected into R5 and OR it with R2. The CSS field is now set to main clock. Let's write it back. The master clock is now officially running off the external crystal. Now we have to wait for the master clock to get ready. Next, we configure the PLL to multiply our clock frequency up to 168 MHz. Now we wait for the PLL to lock onto the target frequency. It doesn't happen instantly. The PLL needs time to stabilize. Before we jump straight to the PLLA, we need to apply the prescaler while we're still running from the main clock. The PLLA gives us 168 MHz, and we're going to divide it by 2 to get our final 84 MHz. And once again, we wait for the master clock to be ready after that change. And the final step, we switch the clock source over to the PLLA. That's it for the clock setup. One more time, we wait. And here's the function epilogue. Pop does the opposite of push. It pulls the values we saved earlier back off the stack and into their original registers. R4 through R8 get restored to whatever they were before we called this function. That's the calling convention we talked about at the start. But notice that instead of popping the link register back into LR, we pop it straight into the program counter. This is a common ARM trick. It restores the return address and actually performs the return in a single instruction. So pop restores all our registers and jumps back to the main in one shot. The function is done and the chip is now running at 84 MHz. Let's move on to our delay function. Here's the start of our delay function. This function uses R4, R5, and R6, so we save them to the stack along with the link register. And we load our loop constant into R4. Then we zero out R5. Move MOV just copies a value into a register. Here we zero out R5. That's our outer loop counter. It counts how many milliseconds we have done so far. Now we start the outer loop. CMP is short for compare. What it actually does is subtract R0 from R5, but it throws away the result. It doesn't store that value anywhere. The only thing it does is update the condition flags in the CPU based on the outcome. So if R5 is less than R0, the result is negative, and the negative flag gets set. If R5 equals R0, the result is 0, and the 0 flag gets set. If R5 is greater than R0, neither flag is set. And we check those flags. If R5 is greater than or equal to R0, it means we have done all the milliseconds we were asked to do. So we jump to delay_done. BGE stands for branch if greater than or equal. And a little later, we'll create the delay_done part. If we're still here, it means we haven't reached our target yet. So we reset the inner loop counter. And here's the inner loop. I compare R6, our inner loop counter, against R4, which holds 8400. If R6 is greater than or equal to R4, we have finished this millisecond, and we branch to inner_done. If we haven't hit 8400 yet, we burn a little more time. NOP means no operation. It does absolutely nothing for one cycle. Then I increment our inner loop counter by 1 and branch back up to inner_loop to check again. Once the inner loop finishes 1 millisecond, we hit inner_done. We increment R5, our outer loop counter, and then branch back up to outer_loop to check if we have done enough milliseconds yet. And here's the exit point for the delay function. Now, let's write our main function. We save the link register onto the stack. Even though main never returns in this program, it runs on infinite loop, we still need LR if we ever want to come back from a function call. Next, we call the clock function. BL calls our clock setup function. It saves the return address in LR and jumps. Next, we enable the clock for PIOB. Now, we take control of pin 27, and we make pin 27 an output. Now, the fun part, the actual blink loop. This is our infinite loop. Everything from here down runs over and over forever. And I turn the LED on, wait half a second, then I turn it off, and wait another half second. Then we go back to the top. And that size is a directive for the linker, not an instruction for the CPU. It tells the toolchain how big the main function is in bytes. And that's it for our Blink assembly file. In the next video, we're writing the startup file. You can download all the files from my GitHub. Link is in the description, and I'll see you in the next video.